We rely on standard formulas to measure the natural world. To find the circumference of a circle, we use c equals 2 pi r. However, elementary geometry has a specific limit. Its tools were developed to measure straight lines and flat planar surfaces. A drafting compass glides in a continuous sweep to create a curve, but the geometry used to measure it is built from rigid, discrete units. To bridge this gap, mathematicians used polygons. They packed curves with straight-sided shapes, increasing the number of sides to create a closer approximation. In mathematics, an approximation is not a proof. A system built on being close enough lacks the structural integrity required for formal deduction. Measuring the physical world accurately required a way to link these discrete shapes to continuous curves. That link was found in the theory of limits. In 1908, Andrei Petrovich Kiselev published Elements of Differential and Integral Calculus. This text provided the mathematical framework for generations of Russian students. Kiselev's curriculum required students to master the formal proofs behind calculus, rather than relying on intuitive shortcuts. He argued that we must move beyond the common idea of a limit as something a variable merely gets closer to. Kiselev defines a limit as a strict boundary applied to a variable quantity. For a to be the limit of a variable x, the absolute difference between them must become and remain less than any given positive number, no matter how small. By following Kiselev's 1908 proof, we can derive the continuous properties of curves through the logic of infinitesimals. This definition provides a mathematical boundary that allows for precise arithmetic on infinite processes. The geometric proof depends on an abstract logical prerequisite, Theorem 17 from Kiselev's Foundations. We begin with two sequences of positive numbers, alpha and beta. As the number of terms increases, every individual term in both sequences tends toward 0. If we divide the corresponding terms in each sequence, the theorem requires that the limit of each individual ratio equals exactly 1. Under these conditions, the limit of the ratio of their combined sums also equals 1. This theorem allows us to determine the behavior of a complex system by analyzing its component parts. We can solve for the whole by proving the smallest individual slices. Theorem 17 isolates micro-scale ratios to provide a macro-scale solution. We can now apply this to the circle to prove its circumference is a unique limit. Kiselev uses an n-sided polygon inscribed in a circle, which is itself enclosed by a circumscribed polygon. We label the inner perimeter P and the outer perimeter P. To find the limit as the number of sides increases, we isolate a single section of the geometry. This is triangle ALL. It contains the inner boundary segment, chord AL, and the outer boundary segment, tangent AL, joined at the central angle A. The relationship between these boundaries is trigonometric. The inner chord AL equals the outer tangent AL multiplied by the cosine of angle A. Rearranging this gives us the ratio of the segments. AL divided by AL equals 1 over the cosine of A. This ratio represents the relationship between the outer and inner boundaries of the slope. We indefinitely double the number of sides. The polygons begin to mimic the curve. As the sides multiply, angle A is forced toward 0. As the angle tends to 0, the cosine of that angle tends to 1. Consequently, the ratio of the outer tangent to the inner chord limits strictly to 1. Because every individual segment ratio limits to 1, Theorem 17 dictates that the ratio of the total perimeters, P over P, must also limit to 1. This allows us to calculate the absolute difference between the outer and inner perimeters. By factoring out the inner perimeter P, the difference is expressed as P multiplied by the quantity of the ratio minus 1. Since the ratio limits to 1, the value inside the parentheses becomes 0. This causes the entire difference between the perimeters to collapse. The mathematical difference between the perimeters reaches 0, and the discrete polygons converge into the continuous curve of the circle. The logic of the bounding limit scales beyond the geometry of a flat circle. We apply this same bounding logic to 3D space. As an inscribed prism's sides multiply infinitely, its volume converges to the cylinder QH. Similarly, by bounding an inscribed pyramid against an outer cone, its faces multiply to form the cone's smooth volume. The logic remains the same whether measuring area, volume, or the surface of a sphere. The discrete faces can decrease according to any progression. They will always yield the same unique continuous limit. Limits allow mathematics to prove the dimensions of the physical world through the convergence of discrete approximations. This leads to the core of differential calculus, the continuous function. In Kiselev's figure 4, we see a curve plotted on a Cartesian grid. This allows us to analyze the requirements for a function to be unbroken. A continuous function requires a strict operational rule. We select point A and introduce increment h on the x-axis, mapping a difference on the y-axis. As h shrinks to 0, the function's output difference must simultaneously shrink to 0. This strict requirement, that an infinitesimal input must produce an infinitesimal output, is the formal definition of a continuous function. By utilizing rigorous limits, mathematics bridged the gap between the discrete arithmetic of polygons and the continuous motion of the physical world.